you are gonna catch right up easily, I think. Basically, we went over the introduction to the paper, which has a big table with a lot of characteristics of the differences between diffuse and discrete aurora, based on a lot of early satellite imaging. So that's one thing that's kind of cool about this vintage article, is that, you know, really it seems like a lot of that definition was coming from these older satellite images at fairly low resolution, both spatially and temporally. So one snapshot of the auroral oval for that whole kind of pass of what it looked like. And in that case, just to remind you guys, typically the diffuse aurora is seen more on the, what we call equatorward side of the auroral oval. And then we're going to get into the more about the discrete aurora this time. So I think that's probably the most interesting part of the article, kind of the heart of the physics of the article. And to repeat the warning of, like, we don't have to understand all of this. We're going to skip some parts, but basically we do try and read section at a time, read around, and discuss what it means. So we can go ahead and get started. Laura, if you can share the article, and then also, I think I'm still waiting to get in on my other computer, which seems like it's possibly, okay, I'm gonna try that. Hold on one sec. New Liz is here. Yeah, so we got through this whole table. We talked about it. The table also talks about how some of the observational characteristics, if you are flying a satellite or a rocket above the aurora, what the particles and electric fields and magnetic fields tend to look like. Okay, so I think we can start here. Apologies, I think I still need the article link, Laura, on this computer. You may have already sent it, but wherever I'm at. Does anyone want to read first?
It's in your Gmail, Liz. Also, River says hi to everybody.
River. Help me in my Gmail. Okay, does anybody want to start? And then we also have, you know, this PDF that you can add comments to as we go. Okay, so there's a nice little section here of the beginning of the article. Go ahead and I'll go ahead and read this because this is an easy little section to read. Okay. I depart from past practice by defining an auroral arc in a fashion suggested by Chamberlain, 1961. When we speak of the aurora, we refer to the visual atmospheric radiation, ... To the physicist, however, a definition of a natural phenomena based on the characteristics of the human eyes seems most artificial. It would seem better to define the aurora with physical processes or prime causes in mind. End quote. There is danger in following this advice, since it is easy to get into the realm of interpretation that later is found to be wrong. The reader will recognize the danger in the following definition of an auroral arc. An auroral arc is the recognizable luminosity resulting from the impingement of a field-aligned sheet beam of electrons or other charged particles upon the atmosphere, the luminosity being approximately proportional to the energy deposited in the energy range, 100 electron volts to 100 kilo electron volts, 100,000 electron volts. The lower border is sharp in consequence of increasing atmospheric density with depth, It has an altitude, typically 80 kilometers to 300 kilometers, defined by the maximum energy of the particles in the primary beam. The vertical extent to the diffuse upper border of the arc increases with the range of particle energy in the primary beam. The range varies from of order 10 kilometers to more than 100 kilometers. This definition is based upon the assumption that the observed luminosity in auroral arcs is the result of particles impacting on the atmosphere. As far as is known, this assumption seems to hold for the nitrogen molecular emissions of the first negative system, but it may not hold for the oxygen 5577 angstrom emission. So this first section is kind of this is a review paper and sort of commentary in the review paper. I'm not entirely sure what he's saying, but I do think it's interesting that he is referring to multiple definitions of an auroral arc and how those are defined to a physicist and not to a physicist. This to me reminds me of a little bit of the debate about whether the Steve aurora is an aurora, of which I am firmly on the side that it is an unusual aurora because the aurora is the light in the sky produced by this whole system. So I don't subscribe to that it's specifically only particle precipitation being the only cause of that. But you can see that this debate goes back further, and I think he'll talk more about this in the article and why there's some debate in his mind about this, possibly because, especially in terms of discrete auroral arcs, this might be a good definition, but when you talk about diffuse aurora, and at the time of this article 40 years ago, the waves that are causing the pulsating aurora specifically don't match this type of strict definition as well. So anybody else have any thoughts on this little section here?
I see a hand up from Mike.
Go for it.
I just had a quick question. When it said like if you scroll up a little bit, it just said like the first nitrogen system. I think this is a chemistry term. Yeah, very beginning of very last sentence.
Yeah.
The nitrogen, so I get individual parts of that sentence, but not together.
Yeah, so the part in the sentence before is that he's talking about the luminosity being proportional exactly to the to the emitted light. So I mean the luminosity is what we measure, but the luminosity being proportional to the energy that's deposited in this specific energy range. And so this is something that people still do the science on, how we can take the luminosity in specific wavelengths, because we know that the auroral light comes out in specific wavelengths. And the finer you parse it, some of these particular wavelengths that the filtered cameras tend to be in, they are advantageous because basically what he's saying is that we've studied how many particles there are causing that light, and specifically for this grouping of nitrogen emissions. So some of the specific altitude of nitrogen, I think probably being the higher altitude, the more blue and red lines. That's proportional, that can be used as a proxy for the energy. These are probably the red lines that he's referring to. And then he's saying that relationship might not be as proportional for the main green line. And so I'm not sure exactly why he's saying it, because I think we today normally do utilize the luminosity of that line as indicative of something about the particle energy coming in. But again, like back at the time, there probably were some observations in this paper that weren't, it's probably evolved since then, as the science does, with several iterations on the research and how you can do that. Does that help?
Sorry. Yeah, I think so. I was just I think in particular I wasn't sure what like the nomenclature means by the first negative system of the nitrogen molecular emissions. Like what is a negative? What is the first negative system? I guess.
Oh, there's different diagrams, like sort of chemistry diagrams that they label. I forget. I couldn't tell you exactly what that means. I would look in Neil Davis's Aurora Watcher's Handbook, if you might have that book. And because I think it breaks out the, this orbital band, there's different labels for those things. So I think it's just a kind of somewhat archaic term for the light that comes out from those transitions.
Okay. Yeah. Thanks.
Yeah. All right. Who would like to read about auroral arc dimensions? This is an interesting part of this.
I can offer myself if you like.
Okay, great. You can read the next, maybe this whole page more or less, maybe a little more if you want.
Okay.
Thanks,
Sounds
Francesca.
good. Yes. A striking characteristic of auroral arcs is the great horizontal length relative to the width. As Figure 1 illustrates, arcs can exceed 1,000 kilometers in length. While it would seem an easy matter to observationally define the width, such is not the case. Discrete arcs invariably have sufficient height extend a few kilometers up to more than 100 kilometers to demonstrate that the alignment is along the direction of the local magnetic field. Consequently, an observation of the width with a remote sensing instrument such as the eye, a photographic or photoelectric imaging device, or a spatially scanning photometer must be made looking along the direction of the local magnetic field. Otherwise, the eye extent of the arc will cause the arc to appear wider than it actually is. See Figure 2. Only if the viewing point is contained between the two magnetical alignment plane bounding the arc can a proper measurement of the arc width be made. Diameters of field-aligned cylindrical structures within discrete auroras can be measured viewing approximately at right angles to the magnetic field. Using this method, Booker et al. 1955 optically observed ray-like structures in active auroras to have diameters 100 meters or less. Stormer, 1955, obtained a value of 7.4 kilometers for the width of a homogeneous arc over Oslo. Arang and Olmon, 1961, reported arc width to 10 kilometers, and Kim and Walkman, 1963, measured 40 homogeneous arc in the geographic zenith. Yeah, I lost zenith at Fort Churchill as having width 3.5 to 18.2 kilometers and average 9.1 kilometers. However, Elway 1957 and Akasofo 1961, among others, reported observing active arcs with thickness of order 100 meters. The extensive measurement of Mag and Davis 1968 of 581 aurora structures appearing exactly in the magnetic zenith at college yielded width from the instrumental cutoff at 70 meters to 4.4 kilometers and median thickness 230 meters. Max and Davis argue away the discrepancy between their result and those reported by Kim and Walkman on the basis that the latter's observation in the geographic zenith prevented them from observing widths less than a few kilometers. Max and Davis stated that their measured width represented the distance between points where the luminosity was 2 to 5% of that in the center of the structure. However, we now know that the image Orticon television they used is capable of detecting a linear structure having rather low contrast with the background. Defining the percentage contrast as being 1,100 times the surface brightness of the structures divided by the sum of the surface brightness of the structures and the background upon which it is superposed. The image Orticon TV can detect structures with contrast as low as 5 or 10%. Consequently, an arc with intensity only approximately 1/20 of the intensity of the background, both wavelength integrated over the passband of the imager, can be detected. The measured width of such an arc will depend on scene contrast rather than the dynamic range of the instrument, as assumed by Magen Davis. In those cases where there is extremely high contrast, the arc being 1 or 2 orders of magnitude brighter than the background, the dynamic range of the instrument could significantly affect the apparent width, as would the profile of apparent surface brightness observed across the arc. The results of Magen Davis should not be taken to imply that the aurora structures they measured were several times or even a decade or two brighter than the background in which these structures were immersed. However, the width measured optically do appear to be realistic, since it is evident that the boundaries of aurora structures exhibit sufficiently steep gradient in luminosity to make the horizontal profile of surface brightness the determining parameter, rather than the instrumental dynamic range or the contrast response in the measured of width. From the way discrete auroras stand out against the background, one is easily misled into thinking that the contrast is much greater than it actually is. The error leads to an apparent contradiction when viewing observation of precipitation electron flux obtained by rocket or satellite traversing the discrete aurora. The apparent contradiction probably disappears when account is taken of the fact that a discrete aurora can be visually or instrumentally distinguished from a background created by precipitating electron flux only 5 to 10% lower.
Maybe we'll pause here.
Yeah.
Thank you. Are you able to give a quicker summary of what you just read about? Not to put you on the spot, or do you have any comments on what they're talking about here? Francesca.
Yeah, I'm just looking again at the article because it's not easy to read and the same time.
No. It's,
yeah, sorry.
You're fine.
For me.
As I was kind of following it, and I'm kind of familiar with some of the probably background history of this, but just to summarize it in plain language, the question is about the dimensions of the auroral arc. And so there's length, width, and height that are the main dimensions we care about. And first they talk about the length being thousands of kilometers. It's actually really super difficult, probably unless you're looking from space, to really truly measure the length of those arcs. And secondly, the width, that dimension is what you see when you look up. And so typically I would say for people from lower latitudes, like most of us are, if you're not in Alaska, you're not going to see the width unless the aurora has come to where it's nearly overhead. But I'm wondering if some of you folks who've seen a lot of aurora have noticed that when the aurora is overhead, there's a pretty narrow width to the aurora. And that's what they kind of get into in this whole discussion is, well, how narrow is it? And they start with some of the older measurements. If you can scroll up, Laura, they talk about further up the Stormer observations and, you know, basically showing that right there, the width of the aurora is about 10 kilometers when you look straight up. And then these folks from Alaska had a little bit better cameras and narrower. Well, they really probably were able to do a bit better because they were able to digitize the observations and start to get a little more precision on that with their instruments. So the Maggs and Davis observations, basically what's found is when you have the ability to get a higher resolution camera, you find that those arcs are even narrower and narrower and narrower up to pretty much the resolution of that new camera. So that's kind of happened even since this article has been written, I'm aware of. There's a good paper by Knutson about auroral arc widths. And Laura, if you scroll down a bit, right here. Okay, stop. This paragraph is important. The one, actually, if we can just see this whole paragraph where they're talking about right there, 7 kilometers down to 70 meters. So you can see that there's a much factor of 10 smaller width of that auroral arc, which, you know, we know is this, we call it like a sheet of current, a sheet of electrons. And so those electrons are following the magnetic field lines all along this distance, this length of the arc. And how narrow is that? That's actually an interesting question. So I'll pause there and see if anybody has any thoughts on narrow arcs or pictures of narrow arcs or additional questions.
I know when you can look up into the zenith, I never stop to think that how actually narrow it is, but yeah, that's what you see. That's incredible when you're looking at it at a distance. Then you have no idea. But another thing where it talks about that there's really not that much of a difference in brightness between itself and the background, and like we can pull that brightness out with our cameras, but visually that sure makes a difference as to what you can see.
Right, and it also would make a difference as to what the measured width would be. So that's another good point that he starts to get into in this next paragraph, where they're talking about how they are technically measuring the peak of the arc, because basically in order to get this width, you need, like if you picture the arc in your picture and just convert that in your head to like luminosity or something, you're going to get some kind of peak. And you could have a peak with very narrow edges. And this is actually what he shows in the figure. So I think it's the figure on the next page, Laura. Yeah, this scroll down just a touch here so we can see the caption. Okay, so these are the parallel auroral arcs. This is a crappy picture, you know, in this old reproduction here, but you can see how, and you can imagine that, you know, if your camera, if you expose it for longer, you're going to get more light there. It's going to fuzz out those edges a little bit. And so you might get a different measurement if you're trying to measure the width across these arcs. And so they start to get technical about this is the center of the arc. Here is where the peak luminosity is, and 2% of that luminosity. So if you convert these into numbers for how bright this is, 2% of that is really where they pick the edges of the arcs and that sort of thing. So let's continue down. This is an extensive background on this. And then they talk more about how we, more about some of the observations. Anybody have any other questions before we go on? It's going to get a little more technical here, but then we'll be, I think, done with this part, this section. So, and we're trying to get to the cool part about the curls and the folds. That's what I want to get to. I'm trying to, Laura, do you want to go ahead and read?
I certainly can, but are we skipping anything, or where are we starting?
Where did Francesca leave off here?
I
5 to
had
10% lower is where she
Yeah,
left off.
okay, cool, thank you. I was like, I had it was in the middle of the page.
Yeah, and then we're almost done with this section. So you can read to the end of this section.
Got it.
And I think that'll be good. Some of it's going to be, yeah, it'll be good.
Okay. That agreement can pertain between ground-based imagery and rocket-borne measurement of electron flux is demonstrated by the results of Johnston and Davis, 1974, shown in Figure 3. The results presented there are unique in that both ground-based and rocket measurements were rather precisely on the same magnetic field lines, such observations being difficult to obtain. There are a number of papers in the literature reporting simultaneous optical and particle measurements that may appear to conflict with statements made here or elsewhere. In at least some cases, the apparent conflict is the product of low resolution in the optical measurement or in the inability to view in the direction of the local magnetic field. The topic of the width of discrete arcs is worth close scrutiny because of apparent differences in the widths of auroras observed optically and the impression one obtains of the generally broader width of causative particle distribution above discrete auroras. Discrete auroral arcs can be very narrow, down to a few tens of meters. And in fact, most active arcs are narrow, of order 100 meters. Multiple arcs, such as shown in Figure 2, are frequently observed. Such an array of arcs viewed away from the magnetic zenith, or magnetic nadir, if viewing from above, can blend together to give the impression of a single broad arc. One could define the broad assemblage as being an arc with an internal structure. However, the dynamical characteristics of the thin linear structures suggest that the name arc be applied to the thinnest features observed, and the name multiple arc to an observed ensemble, a practice observed by Carl Sturmer many years ago. Visual observers have, over the years, had the impression that weak, homogeneous arcs tend to be broader than bright rayed arcs. This impression may have arisen in part from failure to recognize that, often, the broad-appearing weak arcs were composed of several thin arcs, but the results of Maggs and Davis do show a strong trend toward thinner structures as the brightness increases. 68 IBC 1 or 2 structures averaged 740 meters in width. What's an IBC?
He's putting it at the end of the paragraph here.
Cool.
It's, I don't think, even still used, so we're not going to worry too much about that. But interesting stuff here.
Yeah.
Interesting old
154 IBC2 or 3 structures averaged 335 meters, and 16 IBC 3 or 4 structures averaged 190 meters. IBC refers to the International Brightness Coefficient. See, for example, Valence-Jones, 1974. The altitudes of the lower borders of discrete auroral arcs tend to be in the vicinity of 100 to 110 kilometers, indicating a maximum energy in the precipitated electron flux near about 8 keV. There are, however, substantial variations in the altitude of the lower borders over the range 80 kilometers to several hundred kilometers. There is no observational or theoretical results to conflict with the view that if one knows any two of the 3 parameters, 1, height luminosity profile of nitrogen first negative emissions, 2, the atmospheric model, or 3, the velocity distribution of precipitating particles. The third can be calculated using computations such as those of Rees, 1963, or Berger et al., 1970. Results obtained using known electron beams launched from rockets, Hess et al. 1971, Davis 1974, Hallinan et al. 1978, O'Neill et al. 1978, are in accord with this view. Incidentally, the observed diameters of artificial auroras produced by the electron beams are found to be small, from 30 meters to perhaps 200 meters, and thereby demonstrate that electron beams can be propagated hundreds to thousands of kilometers in the Earth's magnetic field without being spatially dispersed. On the other hand, Hallinan et al. 1978 have presented results indicating that conditions causing spatial dispersion do sometimes occur. So
excellent. Sorry, I didn't realize I was unmuted here. I'm going around. Yeah.
My understanding of that is that when you see arcs, they're little tiny thin bands smushed together like layers in a cake. And sometimes your eyes kind of blur it and you see one cake when in fact it's many layers of cake.
Yeah. Mm-hmm. I put a comment in here, and everyone feel free to put a comment if something is clear or unclear or whatever. He's talking about how you can compare ground-based imagery of arcs and rocket-based measurements of the particles coming down the field lines and line them up, which is actually in one of the figures here. But he's sort of also saying that there are a bunch of other papers that claim simultaneous optical and particle measurements, and may or may not be truly simultaneous. And that is a fairly good, valid caution, still prevalent today. We do the best we can, but sometimes there's uncertainty about how close you are on the same field line. So that's sort of my interpretation of what he means there. Yeah, so let's keep going down. Anybody have any other comments or questions here? Okay, too far down maybe. Yeah, if you look at the figure, do you guys want to get into the figure here? So the key part of the figure is this, you can't see my cursor, can you? This plot, the bottom part of the plot is what we want to look at. And two things are plotted on the bottom part of the plot. Actually, multiple things are plotted on this plot. The y-axis on the left-hand side is the flux of electrons of a specific energy. So there's an instrument that's measuring 2.5 kilo electron volts. And that is the more precise digitized line here.
Liz, for viewers at home, could you please define flux in the context of aurora science? Because it has many.
Sure. So a good analogy for flux is the number of particles. Like if you think about rain, how many raindrops are coming down in a specific, on your head. And the conversion to the technical units here are, the number per square centimeter per steradian, which is an angular unit. We don't need to worry about that, per second, and then also per keV. So but basically it's just like how intense the rain is. So it's a measure of flux. So this is going to take a while to explain, I think, but this is on the y-axis. There's 1 million particles of this specific energy is 10 to the 6 here, 10 to the 7, it's a log scale. So 10 million particles. And then you can see the plot goes up to 10 to the 8th. And these are the rocket measurements of these particles. as a function of flight time from Fairbanks here, I'm presuming, which is also as a function of altitude, because these rockets make a nice parabola in the sky. They go up and come down. And so you can see that what we care about here, maybe I should have started with the other plot, which is the dots that are kind of connected in a curvy bit here. Those are actually not the top plot, the other line on the bottom plot. We're going to ignore the top plot. But yeah, that line, that corresponds to the right-hand side of auroral intensity. So that is a digitized line from photographs where the rocket went through this same like patch. It's either a patch or an arc. I'm guessing it's an arc because that's what we're talking about here. But basically you can see that it goes up and comes down, and that is what we're interpreting as an arc. And you can see that over that same time period, this flux of particles also goes up and comes down in a similar kind of way. They're definitely not one-to-one, but whether things are good agreement or not is somewhat in the eye of the beholder here. So all the main point of this plot to get is that they have these two things, the rocket and the intensity of the image of the arc from the ground, and they are moving together here in this example. And people do this nowadays in a lot. Similar things are still done. So that's kind of why I wanted to highlight this plot. But there's a lot of things on the plot, and I don't know if that really made sense or not. Laura, are you getting a main idea there? They're
you know me in math. you can see it when you can see it, and then sometimes it gets to be too much or too. Oh, Becca raised her hand. I'm going to turn it over to her.
Oh, well, you can continue your thought as well, but I was just
that was it.
wondering with the rocket line, we have kind of, when it goes above the approximate visual threshold, we have kind of 3 bursts of particles that it's flying through, as it appears to be, to me at least. But from the photograph, you don't really have those microbursts. So is that kind of a more mathematical, concrete demonstration of sometimes this one arc is actually several little arcs? Or am I interpreting that kind of incorrectly?
I think it's kind of these auroral observations may not have had the precision to capture those peaks.
Yeah.
But also, yeah, you're right. They could be, are they really 3 arcs that we can't even distinguish? I don't think that's what they're saying, but it's a good question. And you'd have to go back and talk to one of the people who was involved in this, which would be difficult. Although I will tell you guys that I actually worked for Tom Hallinan, who's was a professor at UAF and is still around. So it's, some of his references are here. And this is certainly, you know, largely the Alaska group. Okay, we should zoom ahead here possibly. There's more talk about the spacing between arcs, which I think is also very interesting because it's something that, in my opinion, doesn't get quite as much attention today. It's something that can be measured by our aurora chasers, you know, as well, that, you know, there's distances between arcs and what controls that spacing. Still not fully understood today. I think we should skip that part though. And then this next section on the motions and dynamical developments starts to talk about the physics of the speeds at which these arcs can move and how that is what that means. Let's see, which starts to be interesting, but also pretty technical. And then we talk about the curls and the spirals and the curls. So I think we'll skip the section on the spacing and go to this section on the motions and dynamical developments. Does anybody want to read that?
I can read.
All right, great, thanks.
Do you have any idea of how long, or just want to stop me?
2 or 3 pages here. We'll see.
Okay.
It's going to get a little intense here, but we're here.
Great. All right. Motions and dynamical developments. Here we go. The individual arcs of closely spaced arrays, as in figure 2, frequently show enough irregularity of structure to enable imaging systems to detect motions parallel to the length of the arc. Hallinan and Davis, 1970, reported that when such motions occur, they are invariably opposite in direction across the center of the arc array and are in the sense shown in figure 5. Speeds near 5 kilometers per second are typical when rays are present, and speeds over 20 kilometers per second have been observed. If interpreted as being caused by E cross B, I assume E cross B drift, is that what they're talking about? These motions imply a transverse electric field associated with each arc, and which is directed inward towards the arc. The apparent velocity increase toward the outer portions of an array implies that the field associated with each individual arc extends well beyond the arc so that it adds to the fields of adjacent arcs. The required magnitude of the arc fields would be of order 100 millivolts per meter, sometimes as large as 1,000 millivolts per meter. Cool. Should I keep going under figure 5?
Yeah.
Okay. Also implying large magnitude transverse electric fields in association with active auroras is the finding that auroral rays, at least in many instances, are vortex street structures. Hallinan, 1969, Hallinan and Davis, 1970. Auroral rays seen from a point directly down the magnetic field line can be observed with high-speed imagers to develop in the manner shown on the right-hand side of figure 6 into arrays of interconnected spots, such as shown in figure 7. Hallinan termed these structures curls and showed that their development could be described by dispersion relation for the Kelvin-Helmholtz instability for shear flow in an incompressible fluid. Using the fact that the space charge in a sheet is synonymous with vorticity, one obtains the transverse electric field necessary to provide the observed rate of curl development. The result being that fields of several hundred to 1,000 millivolts per meter are required. The curls are always observed to wind up in a direction requiring an inward directed electric field, i.e. a negative space charge. The rotation sense is counterclockwise, seen looking anti-parallel to B in both north and south hemispheres. The requirement for large magnitude transverse electric fields to explain the rapid horizontal motions and development of curls was in conflict with a ground-based, rocket-borne, and low-altitude satellite observations showing that the required electric fields do not exist in the auroral ionosphere. Incoherent scatter radar observations, Banks et al. 1974, direct probes, Axon 1969, Potter and Cahill 1969, Moser and Follison 1970, Gurnett and Frank 1973, Maynard et al. 1973, Maynard et al. 1977, and drifts of barium ion clouds, Westcott et al. 1969, all indicate low altitude electric fields rarely exceeding 100 millivolts per meter, and most indicate a reduction in the field magnitude toward the center of the aurora. Contributing to the resolution of the conflicting evidence on the nature of the electric field associated with discrete auroras were results obtained from high-speed barium plasmas injected onto magnetic field lines with the rocket-borne shaped charge technique, Westcott et al. 1974, 75, 76A. Just as the highly sensitive image orthicon and similar electronic imagers have allowed observation of the intricate details of the dynamical morphology of auroral forms, these devices have made it practical to observe at large distances the relatively weak emissions from the rocket-borne barium plasmas. In applying this method, barium ions are ejected upward along the direction of the magnetic field at speeds in excess of 10 kilometers per second from an altitude above most of the atmosphere, typically above or equal to 450 kilometers. With shaped charge assemblies weighing near 20 kilograms and containing a liner of barium weighing near 1 kilogram, existing imaging systems allow a tracking of the resultant barium jets beyond an altitude 20,000 kilometers and with a temporal resolution of several seconds.
Okay, maybe we should stop here.
Yeah, a lot of stuff.
The barium part is somewhat of a segue into, those are artificial aurora. And so basically they were kind of trying to test their theories about how the aurora can curl up and, you know, where the processes happen to control that using these artificial aurora, which is really cool, but maybe not the primary part of what we're talking about. If you go up to the first, the previous figure, perhaps, Laura. Okay, so here, yeah, this is an interesting sketch. Like, all that we're trying to talk about here is when arcs are moving parallel to the arc length, that there's faster motion kind of on the north side of the arc, and faster motion on the edges of those arcs, which is interesting. And that it also is opposite in direction, so that it goes east on the north side of the arcs and goes west on the south side of the arcs. And this is a consequence of, you think about the magnetic field is kind of into the page in this whole, in this sketch, and then where the electric field is as well. There's a bunch of different electric fields that are important to this also. So, but without totally describing all of those, where we start with here is those two motions. And Donna, like, I think this is even something you could observe, possibly, that, or probably have observed, that the edges of the arc system, if there's an arc system, those edges are what are going to move the fastest and perhaps in opposite directions. And then on the next figure, and they have some different terms for these. So Hallinan was describing how this happens and how that causes these arcs to curl up. He calls them vortex streets. There's a bunch of different terms for, like, fluid dynamic sort of terms. And they're talking about how that's one theory for how this happens. We probably have to keep reading the article to keep talking about the difference between the spirals and the curls. Or no, maybe that is this figure. Hold on. I just need to see the caption more. Yeah. But basically that there's two different phenomena happening depending on the way these electric fields especially get set up to kind of move the arcs around. And when that happens is often during an active time of an auroral display. So things are happening out in the magnetosphere, and yeah, it's kind of interesting. It's definitely pretty technical here, but we can talk more about this. Anybody else want to describe this better than me or ask other questions about it?
Liz, I just want to make a time check. We are
Yes.
at 12:57, and I believe we have a meeting right after this.
we do have a meeting right after this. What meeting do we have right after this? We have
Our
something.
discussion of Tech Talks, I believe.
Oh, no, I think that's in an hour,
Oh, okay, never mind.
isn't it?
I
Um,
can't look on my computer
Yeah,
because I have
I think
the
that
screen
is
share.
in an hour according to my calendar,
Double check.
which should be your
I,
calendar.
I do have to leave right away, but one thing I think it says later, a little bit later in the article, is that the spirals are huge and the curls are a lot smaller. And I went through some of my photos and I could see the difference, like the huge spirals
Yeah,
did look different than the small curls.
yeah, that's this next figure 7, especially, that's nicely labeled. And that is one, I think, strength of this article is that because they try and get these characteristics, you know, even though there's a lot of technical jargon and they are going into side tangents about barium and stuff like that, they are making the big point that these spirals are 200 kilometers in diameter and the curls are like 3 kilometers in diameter. So vastly different scale sizes of these two. So, and then the sketch in figure 8 also shows that. Maybe, yeah, I really like the sketch in figure 8. And Donna, were you able to notice the 2 different senses, that the spirals curl one way and the curls curl the other way?
That I didn't take note. They visually did look different, but I didn't stop to take note of the which one was spinning one way or the other. But I will go back to my pictures and have a look.
Yeah, totally. Do that, because I am betting it's this way. And you know, there's a lot of physics here, and we unfortunately are running out of time to get into that. And I know you have to go, but figure 8 especially, like the curls are kind of like ripples in the arc structure, so it just folds into itself. And you know, it's talking about why that happens. Like it's sort of like a curtain, right? Like a curtain can have little folds into itself, basically, whereas the spirals are more these large scale gradients, and caused by the velocities moving in 2 different directions on the 2 sides of a multiple arc structure. So still difficult to figure out from these sketches, but I think that it helps. And I'll look at the article and let us know if you guys want to have another meeting here and keep going with this. There's definitely a few more pages, and it's interesting. It also gets pretty technical, but yeah. What do you guys, how it would be good to keep going, I think.
I would love to hear more. I do have to leave right now,
Sure.
but
Thank you,
this
Donna.
is fascinating. I did assemble some of my pictures, which I thought were curls, and some that I thought were spirals, but I can share them at some point if you like.
Yeah, that would be great. That would be great too. Anybody else have any requests for this? Questions? We'll let you go, Donna. Any of the other physicists in the room here?
Yes, I think we need more time to talk about the E cross B drift, for example. That is a key point here, or the Kelvin-Helmholtz instability that can cause this shear, and then the rolled up that we can see in this sketch. So yes, if we keep this conversation again, we can continue. That could be nice. Yes, to explain more well.
Mm-hmm. All right, great. Any other final thoughts? Thank you, guys. Feel free to keep reading.
There's a historical motif that you see a lot in like Neolithic stuff, sometimes called a triskel, and sometimes there are variations on this spiral. it looks very much like the auroral spiral. And I'm kind of, I mean, just off the top of my head, there are many, many spirals in nature, but kind of wondering if some of that might have originated from observations of these kinds of shapes in the sky, particularly in like the British Isles, where you tend to see it. But there's no way to know.
I don't think the aurora does the triple spiral.
No, but the spiral where it's two things spiraling around one another as opposed to just one line in a spiral is something that you see on a lot of ancient stuff. So,
Yeah. Yeah, no, it'd be interesting if those, you know, if there was a single spiral and it was in this sense in the northern hemisphere. I want to say the spirals go the opposite way in the opposite hemisphere, but now I'm going to have to go think about that as well. So, and it's probably in this article and I should probably know, but that's also interesting. So yeah, thanks.
Thank you, everybody. We really appreciate your being here today, and we'll continue this discussion at a later point.